Ever find yourself staring at the night sky and wondering, like, what is this all made of, really?
Hmm.
Get ready to go down a rabbit hole,
Yeah.
because today's deep dive is all about cutting-edge physics.
Okay.
We're talking about the search for, like, potentially brand new particles,
Right.
the kind that could, like, rewrite our understanding of the universe.
Exactly. And
Yeah.
you don't need a PhD to follow along.
You said it.
Good.
You sent over some research on something called new Higgs decays to Axion-like particles.
Right.
Honestly, the title alone sounds like something out of a sci-fi movie.
It does, doesn't it?
But you assured me it's going to blow my mind.
Because it's definitely a mouthful, but the core idea is actually quite elegant.
Okay.
Think back to 2012 when scientists discovered the Higgs boson. This research explores if the Higgs boson might decay, basically break down,
Okay.
in ways we never even considered.
Okay. So we're not just rehashing old news here.
No.
This is about potentially finding clues to something totally new.
Exactly.
Intrigued. Tell me more.
These potential new particles are called Axion-like particles,
Okay.
or ALPs for short.
Right.
And here's why they're so exciting. Imagine a universe where we don't actually know what makes up most of its mass.
Right.
That's the mystery of dark matter.
Right.
Or think about how the universe seems to be mostly matter with hardly any antimatter.
Right.
ALPs could be the key to solving these puzzles.
Wow, so these ALPs are like the missing pieces in our cosmic jigsaw puzzle?
Yeah, like that.
But if they're so important, why haven't we found them yet?
That's the thing.
What's the holdup?
That's the fascinating challenge.
Okay.
ALPs are predicted to be incredibly elusive.
Okay.
They interact so weakly with regular matter that they're almost like ghosts,
Right.
passing through our detectors without leaving much of a trace. Detecting them directly is practically impossible with our current technology.
So it's like trying to catch a whisper in a hurricane.
Yeah, very much so.
How do you even begin to search for something that's practically invisible?
That's where the Large Hadron Collider, the LHC, comes in.
Okay.
It's the world's most powerful particle accelerator.
Right.
And our best shot at finding evidence of these elusive particles.
Ah, the LHC. It's like the ultimate science experiment.
It really is.
For those who haven't heard of it, how would you describe it?
Imagine taking the smallest things we know of, protons.
Okay.
These are even tinier than atoms.
Right.
And smashing them together at almost the speed of light.
Wow.
The energy released in those collisions can actually create new particles.
So it's like smashing two watches together to see what they're made of.
Yeah.
Except we're doing it with the fundamental building blocks of the universe.
That's a great analogy.
Right.
And this is where it gets really interesting.
Okay.
This new research suggests that by studying the debris from these proton collisions,
Okay.
particularly how the Higgs boson might decay,
Right.
we could find evidence of ALPs, even if we can't see the ALPs directly.
Okay, I'm starting to see the connection. So the
Right.
paper is saying that the Higgs boson could decay into these ALPs,
Right.
which then further decay into something we can detect.
That's it.
It's like a chain reaction, right?
Exactly.
Okay.
And the paper focuses on 4 specific ways this decay process might happen,
Okay.
each one leaving behind a unique signature.
Gotcha.
These signatures involve particles called muons,
Right?
photons,
Okay.
and something called jets.
All right, time to break it down.
Okay.
Muons, if I remember correctly, are kind of like heavier cousins of electrons.
That's right.
And photons, those are particles of light.
Exactly.
But jets, that's a new one.
Okay.
Paint me a picture.
Think of jets, like the spray of sparks you get when you're using an angle grinder.
Okay.
Except instead of sparks, we're talking about a concentrated spray of particles
Yeah.
that are produced when quarks or gluons, other types of fundamental particles,
Okay.
are created in the collisions.
Got it.
Yeah.
So these combinations of muons. Photons and jets act like the fingerprints of ALPs.
Exactly.
By finding those fingerprints in the LHC data,
Yeah.
scientists would have evidence that ALPs were created,
Right.
even if just for a fleeting moment.
Exactly. You're getting it.
I'm trying.
Each combination is like a unique signature.
Right.
Or a calling card.
Okay.
And because ALPs are expected to be so rare,
Right.
knowing what to look for is crucial.
Right.
That's where the concept of branching ratios comes in.
Okay, before we get too far ahead,
Sure.
remind me what a branching ratio is again.
Imagine a Higgs boson is like a choose-your-own-adventure book.
Okay.
It has several different paths. It can take different ways it can decay.
Okay.
And each path has a certain probability of happening.
Right.
Those probabilities are the branching ratios.
So it's like rolling a die to see what the Higgs boson will do.
Yeah, you could think of it that way.
Some decays are more likely than others.
Right.
And scientists are trying to figure out if any of those paths lead to ALPs, even if the chances are incredibly small.
Exactly.
I'm guessing that's where the sheer power of the LHC comes into play.
Exactly.
Okay.
The LHC generates a mind-boggling amount of data
Right.
because it produces so many collisions.
Right.
This is like trying to find a needle in a haystack.
Right.
But luckily, this paper calculates the branching ratios for these ALP decays,
Okay.
giving scientists a better idea of what to look for
Right.
and how often those ALP decays should occur if they exist.
It's amazing how much precision and ingenuity goes into uncovering these secrets of the universe.
It is, isn't it?
But let's be real, even with the LHC, this is still a long shot, right?
Right.
Finding these ALPs is far from guaranteed.
Yeah, so,
So it's a waiting game,
yeah,
but a calculated one.
right.
It reminds me of those nature documentaries where scientists set up camera traps in the jungle,
Right.
hoping to capture a rare animal on film.
Yeah,
They might not get what they're looking for right away,
right.
but each attempt gives them more data and helps refine their search.
Exactly.
So it's like we're all on this big scientific expedition together.
That's a great way to put it.
And we're all kind of holding our breath to see if these ALPs will show themselves.
Yeah, exactly. And just like in those documentaries, even if we don't spot the elusive ALP right away,
Right.
it doesn't mean the search is a failure.
Right. It's about the journey.
Exactly.
It's what we learn along the way.
Yeah. Is there anything else we can learn from these kinds of searches, even if we don't find direct evidence of ALPs?
Absolutely.
Okay.
Each search helps us refine our understanding of particle physics.
Okay.
Think of it like putting a theory through a really tough obstacle course.
Right.
If it makes it through,
Yeah.
we gain more confidence in our understanding.
Right.
And if it stumbles,
Yeah.
it tells us we might need to adjust our thinking or explore new ideas.
Okay, that makes sense. It's like eliminating possibilities
Right.
and narrowing down the search field.
Exactly.
So what's the next step in this grand quest to unravel the mysteries of particle physics? What does the future hold for the LHC?
Well, the LHC isn't just resting on its laurels.
Okay.
There's a major upgrade in the works
really?
called the High Luminosity LHC, or HL-LHC. High Luminosity LHC, it sounds intense.
It does.
Is it just a matter of making the particle beams brighter or something?
It's more than just brighter.
No.
It's like turning the LHC into a particle physics factory.
Okay.
The HL-LHC will significantly increase the number of collisions,
Okay.
giving scientists a much larger data set to analyze.
So even if the chances of seeing these ALP fingerprints are incredibly small,
Right.
this upgrade would significantly increase our odds of actually spotting them.
Exactly.
It's like using a stronger magnifying glass to search for clues.
Precisely.
Okay.
The HL-LHC will be much more sensitive to rare events,
Right?
giving us a better chance of finding those tiny needles in the haystack of particle interactions.
Right.
It's a really exciting time to be a particle physicist.
It sounds like the future of particle physics is incredibly bright.
It really is.
Or should I say high luminosity?
Uh-huh. Very good.
But even with these amazing advancements in technology, I imagine analyzing all that data from the HL-LHC will be a monumental task.
It definitely will be a challenge,
Right.
but a welcome one.
Right.
It's going to require even more sophisticated algorithms and computing power.
Right.
But that's what pushes the boundaries of science and technology.
Right.
It's a collaborative effort that brings together brilliant minds from all over the world.
It's inspiring to think about all the people working together to unlock these secrets of the universe.
It really is.
But let's bring it back to our listeners who might not be particle physicists.
Okay.
Why does all of this matter?
Yeah.
What's the big takeaway here? It's like we're trying to piece together this giant cosmic puzzle, and we might not even know what the final picture looks like.
Right.
But each new discovery, each new piece brings us closer to understanding the bigger picture.
And isn't that what makes it so exciting?
Yeah.
It's the thrill of exploring the unknown, of pushing the boundaries of what we think is possible.
Exactly.
Yeah.
We started out talking about these hypothetical particles called ALTs.
Right.
But this conversation has really opened my eyes to the vastness of what we're still learning about the universe.
It's incredible, isn't it?
Yeah.
It really is humbling when you think about it.
And the incredible ingenuity and collaboration it takes to make these discoveries. The search for ALPs is just one small part of a much grander endeavor.
It really is.
So for our listeners who might be feeling overwhelmed by all this talk of particle physics and high energy collisions, what's the one thing you hope they take away from our deep dive?
I hope they come away with a sense of wonder about the universe and our place in it,
Okay,
even if the details of particle physics seem complex.
right.
The underlying drive is that same human curiosity. We all share that desire to understand how things work, to uncover the hidden secrets of the world around us.
Beautifully said. It's like that feeling you get when you look up at a starry night sky and realize just how much is out there waiting to be discovered.
Exactly.
Yeah.
And who knows, maybe one day, thanks to the tireless work of scientists all over the world, we'll be adding ALPs to our list of known particles, alongside quarks, leptons, and the Higgs boson.
Now that's a future I'm excited to see unfold.
I agree.
It's like the universe is whispering its secrets.
Yeah.
And we're finally starting to listen.
And we're starting to understand. Yeah, it's an exciting time.
I love that analogy. Well, on that note, we'll wrap up this incredible deep dive into the world of particle physics. We encourage you to keep exploring, keep asking questions, and never lose your sense of wonder. Until next time.